This is question 4 from Physics Test 1, Fall 2015 wrapper. So we're looking for dq of this spherical tube, long tube, cylinder. So we're going to use the linear charge density, lambda. The formula for that is Q over L, which is the total charge of whatever object we're working with over the length of the object. So we're doing charge per unit length. So our object is this negatively charged cylinder, and we're going to be, we know the total charge on that is Q and the total length is L. Actually, the total charge is negative Q. And so now we want to find dq. Now another formula to know is dq equals lambda times dz, where dz is each tiny small slice of the total cylinder. So dz is the width of the ring. When we calculate lambda to be Q over L, so we change this formula into Q over L dz. Don't forget our negative sign. And this is our answer. Now a good way to think about this is that we're splitting up the cylinder into a bunch of tiny little rings and multiplying the charge per unit length by dz for each of those rings. So if you added up all of these dq's, it would be the total charge of the cylinder. So there's our final answer, negative Q over L. So now we're trying to determine the relative position vector r for any observation location in any arbitrary ring on that cylinder. So we know r equals r observed minus r source. And this represents going from r source to r observed, so final minus initial. So I'm going to sketch in our diagram again so we have something to look at. Here's our cylinder. The z-axis coming out, going that way. Off to the right, that location right in the middle of our ring is our R source, 0, 0, Z. Let me fix my bracket notation. And then the point we're going to is R observed. And that vector, that arrow is the vector R. I guess the dot should be at the tail of the arrow. And so now we just want to do R observed minus R source. In our diagram above, R observed, we were told to treat that as 0, 0, W. So now we just simply do R observed minus R source, giving it 0, 0, and then W minus Z. And that is our relative vector, relative position vector, R. Okay, so now we need to express the electric field of the ring as each tiny contribution to the ring. So we're going to use that general formula in blue. We don't even need to pay attention to that formula before it for this problem. So dE, each tiny contribution to the electric field, equals, we're going to put in dQ for Q. Let me write that Q as a lowercase q, as we did in part B and C. And then just copy down the rest of the formula, 4 pi epsilon naught, times 1 over, and now our z up in that blue formula doesn't have much to do with the z we've been using. The z is just representing the radius, or how far away we are from that point charge. So our radius, as we found in part B, was w minus z. And so we'll substitute that in everywhere for z here. W minus z squared minus 3, that big R stays the same, that's just the radius of the cylinder. It's a constant. And then over 2, substitute our w minus z again, w minus z to the 4th. And now we'll extend this fraction out a little bit, close that up. But we're not done yet. We need to take that dq and turn it into something we can integrate across, which was dz, as we found in part B. Part A, sorry. So now we found our dq equals negative q over L times dz. Plug that in. And now just copy down the rest of the formula as is. w minus z to the fourth. Close that up, and that's our answer. Pretty proud of that electric field, dE. Actually, but this is still just the magnitude, dz, because I accidentally labeled it dE as a vector up there. But really, this should be we need to add a z hat here to make this a proper electric field vector. So I'll put that z hat in there, and that's our final answer. Okay, so now we need to finally set up our integral to calculate the net electric field from our whole hollow cylinder. So let's figure out our bounds first and what we're exactly integrating across. So here's our negatively charged cylinder. And we've got our axes right here. Z-axis going through, that's the z. And the problem told us that was L over 2 and negative L over 2 respectively. So we're going to be integrating from negative L over 2 to positive L over 2. And now we know our formula for electric field net is the integral of all of the smaller portions of the electric field, dE, and our limits, negative L over 2 to positive L over 2. Now we can substitute our formula from part C. Same limits again. This should all just be pulling straight from part C because we wrote that formula for dE. That's a Q, negative Q. Use our W minus Z squared again. That squared needs to be outside of there. W minus Z, sorry about that. Looks like I'm running out of space. I'll make some up here. To the fourth, close that up, and don't forget our Z hat. Pick another tip that'll work better. Now it's just time to work that integral. So we can pull out a lot of constants to make this easier from the start. For starters, 1 over 4 pi epsilon naught. dz obviously has to stay in there, but negative q over L can come out as well. Q. We can pull out the z hat, and now we'll leave this aside. We'll come back to this later and just finish writing the integral and solve what we have to solve now. So set our dz still in there, and we couldn't pull out the w minus z's, any of those terms, so those have to stay in there as well. Okay, so now we need to think of something we can do to make this integral a little bit easier, because the w minus z term in there is going to be tough. So we can substitute out that w minus z, put in our new variable, take both those w minus z's, we'll substitute for a little r, and define little r as w minus z. So forget it. Let's try that one again. Substitute r equals w minus z. And so from this we'll also get dr equals negative dz. So we'll have to address the bounds on our limits as well as all the variables inside the integral. So let's remember we have all those constants out there from before and just work with the integral for now. So now our bounds are w minus L over 2 and w plus, oh wait, no, the way we're substituting it, the bottom one should be a plus at this point, and the upper bound should be w minus L over 2. And that's because we set r equal to w minus z. And now we had dr equals negative dz, so we'll plug in negative d dz equals negative dr. Plug in negative dr. The rest of our integral looks much simpler now. So now we can start solving this one. The best approach here is probably to first take out these negatives and switch our bounds. So if we can get rid of the negative dr and make this a regular old looking integral, and our bounds switch from w plus to w minus. So now we can solve this as, we can think of it as two separate integrals, one integral minus another. So I'll write it out here just as 1 dr. And now we'll move on to breaking it up and evaluating it. So don't forget about those constants that we had from up above. But now let's start evaluating this integral. So 1 over r squared is, the integral of that is negative r to the negative first. We'll do that from our bounds. And just subtract the other integral, 3r squared over 2r to the fourth. We have to use the chain rule here. Or no, we don't. We just have to keep track of our constants the right way. So 3r squared stays in there. 2r to the fourth becomes negative r to the negative third over 3. Looks like that 3 will cancel, but we'll see that in the next line. Keep our limits in there, our bounds, I mean. And that should be the end of that. Our dr was solved out with the integral. So now let's simplify this expression a little bit. Again, for last time, remembering our constants from before. We can cancel out some negatives here. So those both become positive, making work easier for ourselves. And now our final electric field. Let's bring those constants back down from before. We've got z hat over 4 pi epsilon naught. We have negative q over L. And now let's do some algebra. So we'll take that right-hand term first from the integral. The 3's cancel and we're left with r squared over 2 times w plus L over 2 to the negative third. And just subtract out that other one. We're distributing across that r squared over 2. So there's that first part of it. And now we'll tackle the negative r to the negative first. So we're just subtracting w plus L over 2. So negative first minus w minus L over 2. And again to the negative first. Close that up. Now we can do a tiny bit more simplification here. So I'll copy down what we have. Most of it's the same except for that last part. And so now we can take this last part and turn it into L squared over 4 L squared minus W squared L and put all of that to the negative first. Close it up, and that's the final answer for the net electric field. Cool.